Okay, so we're starting to work through chapter 16 of Colin McClarty's book, Elementary Categories, Elementary Toposes. So this chapter is called From the Internal Language to the Topos. And the idea here is basically that we're going to use the Mitchell-Benabal language to understand more about the structure of toposes themselves. And so let's just dive straight in with this lemma here. And it says that for a pair of arrows, F and G, from an object A to an object B in a topos, we have that F is equal to G if and only if it's always true that Fx equals Gx, where X is a variable of type A. So let's prove it. So what's it mean to say that it's always true that Fx equals Gx? Well, that happens if and only if this extension of Fx equals Gx over X, in other words, the subobject classified by the interpretation of Fx equals Gx, is the maximal subobject of B. It is the maximal subobject of A, and that happens if and only if the identity arrow of A is in such a thing. And then this happens, just working out this interpretation then, this happens if and only if 1b is in the subobject classified by the interpretation of delta b after fx comma gx interpreted over x. So that's just expanding out this term here. And then we can work out this interpretation, so we can rewrite this as the subobject classified by delta b after f comma g, and then we know that delta b is just shorthand for chi of identity b comma identity b, so we can rewrite this as a subobject classified by identity b. So we can rewrite this as the classifying arrow of identity b comma ident. So we know that delta b here is really just the classifying arrow of this diagonal arrow, identity b comma identity b. So we can rewrite this as a subobject classified by chi of identity b comma identity b after f comma g. And then identity arrow of A is going to be in that subobject if and only if we have that chi of identity b comma identity b after f comma g after identity A sends everything to true. And that's going to happen if and only if f comma g is in identity b comma identity b. That happens if and only if there exists a k such that f comma g is equal to identity b comma identity b after k, which happens if and only if f equals g. So that's the completion of this proof, and it's really quite straightforward. In fact, this is really just a sort of Mitchell-Benabal language encoded way of saying that two arrows are equal if and only if they always act the same way on any kind of arrow that you compose them with. So here's another kind of result which is nice. So we could say, and it's a little cryptic maybe to say this, but this next result says that an arrow in a topos is a monomorphism if and only if it's internally one-to-one. Okay, but more concretely, what this really means, this theorem 16.2, we're saying that, say we have an arrow f from an object A to an object B in a topos, well, that's going to be a monomorphism. In other words, it's going to be monic if and only if for our variables x and x dash of type A, we have that x equals x dash always implies fx equals fx dash. So what's the proof? Well, we just sort of interpret this Mitchell-Benabal language basically. So saying x equals x dash always implies fx equals fx dash. Well, that happens if and only if the subobject classified by the interpretation of x equals x dash is contained in the subobject classified by the interpretation of fx equals fx dash. So we just work out those interpretations. So I'm just sort of replacing these equal signs, which is just shorthand now, so we can rewrite this as chi of identity A comma identity A after x comma x dash. That's just expanding out what this means. And similarly, we can expand out what this means to be chi of identity B comma identity B after fx comma fx dash. That's just expanding out what this means. And so we're basically saying that the subobject classified by the interpretation of this on the left is contained in the subobject classified by the interpretation of this on the right. And so working out those interpretations, we're basically saying that the subobject classified by chi of identity A comma identity A after P1 comma P2 is contained in the subobject classified by chi of identity B comma identity B after FP1 comma FP2. Now we can rewrite this subobject on the left here. That P1 comma P2 is just going to be the identity arrow, so we can ignore that. And then we've just got the subobject classified by chi of identity A comma identity A, which is just identity A comma identity A, the diagonal arrow of A. So we're basically saying that that's contained in the thing on the right. That's equivalent to our initial statement. Now we can rewrite this now because we're basically saying that one subobject is contained in another. So an equivalent way to say that is for every arrow I comma j from subobject h into A times A, we have that I comma j is in the first object. So we have that I comma j is in the first subobject implies I comma j is in the second subobject. So basically this thing's equivalent to saying that I comma j is in identity A comma identity A always implies I comma j is in the subobject classified by chi of identity B comma identity B after f of P1 comma f of P2. Now that first part, this is just saying that I equals j, like I comma j is equal to I, like basically I'm saying that I comma j is in identity A comma identity A if and only if I equals j. So this first statement's basically just equivalent to saying that I equals j. So we can rephrase this whole thing. It's basically saying that I equals j implies that I comma j is in this black subobject here. But another way to say that is that this thing inside the brackets, which is the classifying arrow of the subobject, doing this after I comma j sends everything to true. So this whole statement up here is equivalent to saying that I equals j implies chi of identity B comma identity B after fp1 comma fp2 after I comma j is equal to true after exclamation mark h. And that happens if and only if I equals j implies f after I comma f after j is in identity B comma identity B. And this happens if and only if I equals j implies f after I equals f after j. And this obviously must hold for any I comma j from h to A times B for any h. So this basically happens if and only if f is a monomorphism. That's our definition of a monomorphism. So we've proved the results. We've shown that this kind of Mitchell-Benebawi statement holds if and only if f is a monomorphism.